cell converts light into electricity. This solar cell, when placed under the sun, can generate 9 amps of current. But we need an electrode in the form of a printed metal grid to extract all that current in an efficient manner.
Most solar cells today feature an H-pattern front metal electrode which is designed to carry current along fingers and ribbon bus bars. All the current is carried out of the cell via the ribbon connections at the front. An interesting alternative is to create through holes in the solar cell and then route the current to the through holes to the back of the cell. This is called the metal wrap-through solar cell, or MWT for short. MWT cells have two advantages over conventional H-pattern cells. First, you'll notice in the MWT cell the current never has to travel very far to the nearest through hole, so that all the current can be carried by thin fingers that don't shade the active areas of the cell from light as much. Second, since the current is routed to the back, all the interconnections of the cells inside a solar panel can be done on the same side, which can be simpler. One last point may be a bit subjective, but a lot of people say that the metal patterns of MWT cells are more visually appealing. Certainly, there can be a much greater variety of designs for MWT metal grids, and the design process is a great way to learn about how to create an efficient solar cell. So let's get started with our very own MWT front grid from scratch. A good solar cell needs to gather up current that's generated from all across the cell plane. Here we draw one section of the MWT cell with a through hole in the middle of it. Here Clara is drawing a front metal grid which is sprawling out from the middle like the roots of a tree. The analogy is pretty good in that the photo-generated current trickles out of the cell plane like water, and the metal grid acts like conduits to collect and carry the water out to the external circuit. So in-house we got custom editing softwares to modify the line widths of our metal grid section and to turn it into common CAD formats like AutoCAD DXF. Just give us a shout if you're interested to learn how to do it. This will enable us to render the drawing into accurate formats that we can simulate, and we can then manufacture solar cells with the designed pattern. Now, we're loading the AutoCAD DXF into Griddler 2, which is a finite element simulator dedicated to solving the solar cell planes, available for free online. We can quickly have a look at the voltage distributions on the cell section that we designed. A well-designed grid enables current to flow smoothly to the middle through hole, and we need to look out for pockets of space where the cell voltage is unusually high, which could be indicative of a clog. And here we don't see any, which means the design is okay. Next, we can simulate the IV curve of the solar cell section with such a front grid. For the cell parameters we have chosen, we end up with quite healthy numbers and a predicted efficiency of 19.53%. Earlier, when we loaded the pattern, Griddler told us that the amount of shading brought about by the metal grid is 4.85% of the cell area, which is a tad bit high for an MWT cell and is definitely an area of improvement. Meanwhile, the fill factor exceeds 78%, which is a good sign that the current on the cell front plane is conducted to the through hole in an efficient manner, so that series resistance losses are not much of an issue. So actually, in the full area solar cell design, our metal grid pattern is repeated 16 times over the whole face of the cell plane, and there are 16 through holes, each responsible for collecting the photocurrent generated in its own section. Here's a little animation of the cell voltage as the IV curve is swept from short circuit conditions to the maximum power point. There you have it, guys, a virtual MWT cell in 3 minutes, from the drawing board to finite element simulation, and ready for implementation in the production line. Let's also have a look at a collage of other MWT patterns that we or other researchers over the world have designed.